This is Dr. Christy Patton-Lukes, and in this video lesson we're going to be looking at latent heat changes. These are going to be the phase change, enthalpy, and internal energy changes. So phase change operations are going to be vaporization, fusion, and sublimation. We've already looked at these in the past, but just as a quick refresher, if you look at pressure versus temperature, you'll find that you have solids and gases at the very low pressures and temperatures separated by the sublimation curve. This ends at the triple point, and then we have a region that separates gases and liquids separated by the vaporization curve that ends in the critical point, and then solids and liquids are separated by an arc that does not have a particular end, and that just is going to separate out solids and liquids. That's our fusion or our melting curve. The energy changes associated with these are going to be latent heats, and we're going to be talking about both internal energy and enthalpy, so H and U. But what we have in mind, the mental picture you should have, would be to look at a graph of, say, temperature versus volume for a pure substance. And you have this picture already in your heads, I hope. These are these curves that look something like this. They end at the critical point, which is the highest temperature and pressure, where you can have the two phases coexist. I have liquids over on this side, I have gases over on this side, and I have liquid-gas combination in the middle. And the idea is that if I choose a fixed pressure, let's say 1 atmosphere, and looked at a particular substance, as I increase the temperature, the volume will increase, and then it will reach a stage where it will change, the volume will change very rapidly, but temperature will stay the same. And that's the vaporization. And then as I continue to increase the temperature, the volume will increase fairly rapidly at that point. So we want to talk about this vaporization where it goes from one corner to the other corner of this dome. And this is the image we have, which was temperature versus volume. But instead of volume, I could have replaced this with enthalpy, or internal energy, or entropy, any of these various functions. If I were to choose enthalpy, then the distance between these 2 points, the length of this line segment here, is going to be the heat of vaporization. So delta H of vaporization. And the way they write it in this book is delta capital H with a little circumflex on the head, sub V for vaporization, and it's the difference between the enthalpy of the saturated vapor and the enthalpy of the saturated liquid. If we were to do the same thing with internal energy graph, it would be the difference between the internal energy of the vapor and the liquid, and that can be approximated as the enthalpy of vaporization minus RT. And I can do these same kinds of things for any of these various phase transitions. So for fusion, it's the liquid minus the solid, and for sublimation, it's vapor minus solid. So it's always the order of subtraction is so that you get a positive answer for this enthalpy change. And we can relate enthalpies and internal energies using the rules from the previous lessons. Now we can find these latent heat values in data tables. Perhaps we have just simply we know the enthalpy of the saturated vapor and of the saturated liquid, and I can subtract. Okay? And these are going to be a function of temperature, because if we look at this curve, and I'm going to draw it again over here, and let's think of this as H this time. Up here, the length of that line segment is very different from what it is down here. So delta H is a function of temperature. Okay? Frequently, what we're going to have is limited data where we have perhaps at one say the normal boiling point when pressure is 1 atmosphere, will have only that one value for the latent heat for any of these substances. So how can we estimate delta H for vaporization, fusion, sublimation? Well, we have several techniques. Some of them are better than others. We have a very simple-minded rule, Troughton's rule, which is very simple. It's not very good. It's kind of a desperation measure. Okay, so I would say use in desperation only. If you have nothing else to go on, use this. And so what you need is you need the boiling point, and just take the boiling point in Kelvin, multiply by 0.088 if it's a nonpolar liquid, and 0.109 if it's a polar liquid. And that will be a quick estimate of the heat of vaporization. It's not really a good estimate, but like I say, sometimes you just have something and you have no idea where to get started. This will at least allow you to do calculations. There's also something called Chen's rule, which is actually pretty good. It's going to be plus or minus 2%. There's a minus underneath there. If you use temperature in Kelvin and pressure in atmospheres, this will get you a heat of vaporization in kilojoules per mole. So you're going to take the boiling temperature divided by the critical temperature and multiply that times 0.0331, and then subtract 0.0327 from that, and then add 0.0297 times the log base 10 of the critical pressure. All of that is going to be multiplied by the boiling point, and then all of that will be divided by the quantity 1.07 minus the boiling temperature divided by the critical temperature. And this will estimate the heat of vaporization. Now the boiling temperature here is for the pressure that you are operating at. So this isn't necessarily the normal boiling point. If you are operating at 1 atmosphere pressure, then it would be the normal boiling point. But whatever temperature that you are trying to calculate, this will get you heat of vaporization for that estimated temperature. And again, it's usually pretty good. It's typically plus or minus 2%, which is actually quite nice. Now for heat of fusion, we only have a very, very rough estimation technique, okay? Depends on what type of solid phase you have being formed. And so metallic elements, organic compounds, and inorganic compounds are the breakdown here. And again, it's just you choose the proper multiplier times the melting temperature in Kelvin to get you a very rough estimate of heat of fusion. This is not going to be a great answer, but we tend to use this one a little bit more often because frequently we don't actually have good data here. So if you have data, that's certainly the best. Let's find data. Let's look in the appendix of the textbook or other sources and see what data we can find in this case. We've got liquid benzene transferring to gaseous benzene. So we're going to be looking at benzene. We're going to be looking at both the liquid and the gaseous phases. And we're going to have a process that's going to have this phase transition. So we're going to need heat of vaporization and boiling point data to do this. Okay, so we have our data now. Some of the things that we need to note is that I have a heat of vaporization value given. It's at 80 degrees C. And I have C sub P for liquid benzene, but it only is valid up to 67 degrees C. So this is going to cause sort of an issue for me. I need to use the C sub P. I could try extending the range, but sometimes that's really, if they give you a very specific number, there's probably a really strong reason for why they did that. And so instead, I'm going to use Chen's rule to estimate heat of vaporization at 67 degrees C. So Chen's rule And I'm not going to bore you with writing those numbers or the calculations. But that estimate says that delta H of vaporization is going to be 27.3 kilojoules per mole at 67 degrees C. So now then, using this instead of this one up here, I will be able to create a path that's continuous. So my path is I'm going to start at 20 degrees C, 1 atmosphere, and it's a liquid. And I'm going to take that to liquid at 67 degrees C, 1 atmosphere. And then I'm going to have that phase change. So I'm going to now change this to vapor at 67 degrees C, 1 atmosphere. And then I've got this vapor at 67, so I'll go ahead and heat the vapor to 100 degrees C, 1 atmosphere. And then I'm going to change the vapor from 100 degrees C, 1 atmosphere to 100 degrees C, 3 atmospheres. So I've got several different steps here. 1, 2, 3, 4, various steps. Step 1 is going to change temperature for the liquid. So delta H1 is going to be from 20 to 67 degrees C, C sub P for the liquid, dt. And I'll have to integrate that. And let's see, when I did that earlier, I came up with 6.4 kilojoules per mole. Delta H2 is going to be for the phase change. So this is going to be the heat of vaporization. So that's 27.3 kilojoules per mole. Step 3 is going to take the vapor from 67 to 100 degrees C at constant pressure. So delta H3 is going to be from 67 to 100 in Kelvin, C sub P for the vapor, dt. And when I did that, I got 3.3 kilojoules per mole. And then my final step is just the pressure change. And for gases, this is going to be essentially 0. And so my total delta H is the sum of these, so 37.0 kilojoules per mole. Now, keep in mind, this is not the only possible path. This is a choice of path. Different ones will get different answers, but they should all be very, very close to being the same answer. So you might try doing this on your own, choosing some other rational paths, okay? Maybe you wanted to have the phase change happen at the very beginning at 20 degrees C. And then you'd only have to integrate the C sub P for the vapor from 20 to 100 degrees C, and then do the pressure change. So there are some other paths that you might choose that might simplify the calculations. Your answers should be very similar, as long as you don't go crazy with your significant figures. So this concludes our lesson on latent heat of vaporization. In our last lessons for this unit, we're going to be talking about some other kinds of energy changes that we will have, in particular psychrometrics, air and water, and mixing. So why they always give you the rule, always add acid in a chemistry lab course.